4 billion miles from the Sun, a tiny frozen world is doing something that sounds almost impossible. Pluto appears to have a natural cooling system. Its own atmosphere contains a thin layer of haze that may be helping the dwarf planet lose heat and become even colder than scientists once expected. And the strange part is that researchers did not discover this by sending another spacecraft there. They uncovered it by studying the faint infrared light reaching us from billions of miles away. To understand why this matters, we have to go back to the beginning. In 1930, Pluto was still unknown to humanity. At an observatory near Flagstaff, Arizona, a young astronomer named Clyde Tombaugh was searching through photographic plates of the night sky. The method was simple, but incredibly tedious. He photographed the same region on different nights and then compared the images, looking for anything that had moved. Stars appeared fixed. A planet would shift. And after countless hours of searching, one tiny point finally revealed itself. Something was moving. That faint object became Pluto. For decades, Pluto occupied a special place in our understanding of the solar system. It was taught as the ninth planet, the mysterious world at the edge of the planetary family. But there was a problem. We knew almost nothing about it. From Earth, Pluto was little more than a tiny point of light. Astronomers could follow its orbit and estimate its distance, but its actual surface remained hidden. We could not clearly see its mountains, its valleys, its atmosphere, or the strange chemistry taking place across its frozen landscape. Even Pluto's size was once badly misunderstood. Early calculations suggested it might be much larger than it actually is. Some scientists even believed its gravity could help explain irregularities in the motions of Uranus and Neptune. Later observations showed that those supposed gravitational effects were not caused by Pluto at all. So for much of the 20th century, our picture of Pluto was built from limited evidence and educated guesses. Then came 2015. After traveling through the solar system for more than 9 years, NASA's New Horizons spacecraft finally reached Pluto. It was moving at tens of thousands of miles per hour. There would be no second attempt. New Horizons was not going to enter orbit and spend years circling the dwarf planet. It was going to fly past, collect as much information as possible, and continue outward into the Kuiper belt. For scientists, the encounter was a once-in-a-generation opportunity. And Pluto immediately shattered expectations. Instead of the dead, featureless ball many people had imagined, New Horizons revealed an incredibly diverse world. Across its surface was a giant pale region shaped roughly like a heart. Inside that enormous basin were landscapes that looked remarkably young compared with much of the surrounding terrain. Elsewhere, mountains made largely from water ice rose several miles above the surface. At Pluto's temperatures, water ice behaves nothing like the ice we experience on Earth. It becomes extremely rigid and can act more like bedrock. Then came another surprise. New Horizons detected broad regions covered in nitrogen ice. Some areas showed patterns suggesting that the frozen material could slowly circulate, creating enormous convection cells. That meant Pluto might still be geologically active. Above the surface, New Horizons also photographed a thin blue atmospheric haze extending hundreds of miles upward. This was perhaps one of the most visually striking discoveries of the mission. Pluto was not simply an ancient frozen rock sitting motionless at the edge of the solar system. It had weather. It had an atmosphere. It had mountains. It had changing surface chemistry. And it appeared to have an interior that might still contain enough energy to reshape the world. But New Horizons had one major limitation. It only got one close encounter. Once the spacecraft passed Pluto, it continued deeper into the outer solar system. It could not turn around and return for another detailed inspection. That meant scientists were left with an enormous amount of information, but also enormous numbers of unanswered questions. What exactly was happening inside Pluto's atmosphere? Why was its haze so extensive? How was the atmosphere interacting with the surface? And most importantly, how was Pluto actually losing and gaining heat? Answering those questions required something different from a spacecraft flyby. Scientists needed an instrument capable of studying Pluto's light in extraordinary detail. That is where the James Webb Space Telescope entered the story. Webb does not need to travel to Pluto to study it. Instead, it analyzes the light arriving from that distant world. Light is not simply something we see. It carries information. When scientists separate light into its different wavelengths, they can search for patterns associated with specific molecules. Those patterns act almost like fingerprints, allowing researchers to determine what chemicals are present and how different parts of an atmosphere behave. For a world as faint and distant as Pluto, this is an extraordinary technical challenge. And there was another complication. Pluto has a large moon named Charon. From our perspective, Pluto and Charon are close together in the sky. Separating their faint infrared signals requires extremely sensitive instruments and careful analysis. Older telescopes struggled with this problem. The signal from Pluto was incredibly weak, and separating it cleanly from nearby Charon was difficult. Webb's infrared capabilities changed that. Beginning with observations made after the telescope became fully operational, scientists were able to examine Pluto in wavelengths that revealed information that visible light observations could not provide. And one particular feature immediately became important. That blue haze. New horizons had already shown us that Pluto's atmosphere contained complex hydrocarbon particles. But scientists wanted to know what role those particles actually played in Pluto's climate. Could the haze simply be an atmospheric byproduct? Or could it actively change the temperature of the world beneath it? Years before Webb's observations, researchers had proposed a fascinating possibility. Instead of acting like a blanket that traps heat, Pluto's haze could actually help remove heat from the atmosphere. The mechanism sounds strange, but the basic idea is surprisingly simple. Particles high in the atmosphere absorb incoming energy and later release that energy as infrared radiation. Some of that radiation escapes directly into space. If enough energy is lost this way, the atmosphere can become significantly colder. In other words, Pluto's haze may function less like a blanket and more like a giant atmospheric radiator. A natural cooling mechanism operating billions of miles from the Sun. And when Webb provided new infrared measurements, the observations supported this general picture. Researchers found evidence that Pluto's atmospheric haze plays an important role in cooling the atmosphere, producing temperatures lower than many earlier models had predicted. The estimated effect is significant, roughly tens of degrees Fahrenheit colder than previous expectations. That makes Pluto's atmosphere unusual even by the standards of the outer solar system. Its extreme cold is not explained simply by distance from the Sun. The atmosphere itself appears to be helping Pluto shed energy. And that raises a much larger scientific question. If this process occurs on Pluto, could something similar happen on other distant worlds with hazy atmospheres? One possible comparison is Triton, Neptune's largest moon. Triton is also extremely cold, also has an atmosphere, and also contains complex atmospheric chemistry. Studying Pluto therefore gives scientists a natural laboratory for understanding how thin atmospheres behave under conditions very different from those found on Earth. But the haze has another story to tell. Its chemistry is connected directly to Pluto's surface. Even though sunlight at Pluto is incredibly weak compared with what Earth receives, It still provides enough energy to trigger chemical reactions high in the atmosphere. Methane molecules can be broken apart by ultraviolet radiation. The fragments then interact with one another and form increasingly complex carbon-rich compounds. Eventually, some of these compounds become larger particles known as tholins. And these particles slowly descend toward the surface. Over enormous periods of time, they contribute to Pluto's reddish and brownish coloration. This process is extremely slow. But Pluto has had billions of years.